Polyethylene is the thermoplastic polymer consisting of long chains of the monomer ethylene C2H4. Polyethylene is one of the most widely used plastics in the world, known for its versatility, durability, low cost, and chemical resistance. Polyethylene appears in countless product and industrial applications. Polyethylene comes in several major types, each with different structural characteristics and performance properties. These variations allow PE to serve many different functions, from the flexible packaging to the strong, rigid component. There is four products of polyethylene. First is high-density PE, HDPE. Polymer chain is linear and no or less short branch, so polymer chains pack closely together. Therefore, it has higher density. Second, linear low-density PE, LLDPE. LLDPE is produced by copolymerization ethylene with alpha olefins such as butane 1 hexane 1. It is linear polymer with a number of short branches. Therefore, polymer chains do not easily pack together. As a result, it shows lower density. Third is low density PE, LDPE. It has higher degree of short and long chain branch, so the polymer do not pack well. Therefore, it has lower density. Lastly, ultra-high molecular weight elastomeric polyethylene, UHMWPE. Thermoplastic elastomer with a very high molecular weight that provide exceptional toughness, impact strength, and elasticity, making it suitable for applications requiring both durability and flexibility. Next, its significance in various industries. First, packaging, the primary application globally used for the plastic bag, films, food wraps, due to its moisture resistance, durability, and low cost. Second, constructions, used for durable corrosion resistance pipe for water and gas distribution systems, insulation material, and geomembranes for lining landfills and waste containment system. Lastly, healthcare or medical, valued for biocompatibility, chemical resistance, and ability to sterile. Next up, we go to the first polymerization method, which is bulk polymerization. Bulk polymerization, as applied to polyethylene production, is a polymerization method in which pure ethylene monomer is polymerized directly without using any solvent or dispersing medium, with only an initiator or catalyst present. In this method, ethylene is subjected to very high pressure and temperature, or appropriate catalysts such as Ziegler naphtha or metallocene, causing the monomer molecule to link together and form solid polyethylene. Because no solvent is used, the process produces high purity polymer, but it's difficult to control the reaction since bulk polymerization releases large amount of heat during chain growth. For key of bulk polymerization, single phase reaction. The process occurs in the homogeneous phase. Change growth mechanism, ethylene monomers continuously add to active change and to form non-PE chains. Exothermic reactions. Large amount of heat are released during polymerizations. Heat control is critical. Efficient cooling is needed to prevent overheating and runaway reaction. High product purity. Absence of solvent leads to polyethylene with minimal impurities. Next up, factor affecting bulk polymerization. Temperature. Higher temperature increases reaction rates, but it can reduce molecular weight and cause runaway reaction if not controlled. Second, pressure. High pressure is required to keep ethylene at a reactive phase and to increase polymerization rate. The type of initiator or catalyst, determine reaction mechanism, polymer structure, and molecular weight of PE. Lastly, catalyst or initiator concentrations. Higher concentration increase polymerization rate, but it may shorten the polymer change. Now, we move into its advantage and disadvantage. Advantage of bulk polymerization. First is high polymer purity. No solvent is used, so there is no need for solvent removal or purifications. Second, simple process setup. Fewer components and steps compared to the solution or suspension's polymerization. Third, high monomer concentrations lead to a high rates of polymerization. Lastly, lower production costs eliminates solvents handling, recovery, and disposal costs. For its disadvantage, first, difficult heat control. The reaction is highly exothermic, increase the risk of overheating or runaway reactions. Second, high viscosity. As the polymer forms, mixing and heat transfer become more difficult. Third, limited temperature control. Poor heat removal can affect molecular weight and product consistency. Lastly, operational challenge at high pressure, especially for free radical PE production, requiring robust and expensive equipment. Products and application of bulk polymer. For product, it produces low-density polyethylene (LDPE), produced mainly by bulk polymerization using free radical initiations at high pressure and temperatures. Second, high purity polyethylene resins, minimal contaminations due to its absence of solvent or dispersive medium. For application, first, film and plastic bags. It's applied in a food container and plastic bags. Second, laboratory equipment, such as water dropper for non-aggressive chemical. Lastly, household goods. For example, is buckets and plastic toys.
Next, we go to the second polymerization method, which is solution polymerization. The definition of solution polymerization: monomers, initiators, and chain transfer agent, if used, are dissolved in a suitable inert solvent. Catalyst, ionic or coordination, can be dissolved or suspended in the solvent. The system is homogeneous, allowing easy temperature control. Reaction temperature is limited by the boiling point of the solvent. After polymerization, polyethylene can be used in solution or isolated by evaporating the solvent. It can produce polyethylene with uniform and well-controlled properties. Now, I will explain the key principle of solution polymerization. First, the reaction occurs in a homogeneous system, where the monomers, initiator, and solvent are completely dissolved and form a uniform phase. Next, the solvent plays an important role in heat dissipation. It absorbs the exothermic heat produced during polymerization, which helps prevent overheating and polymer degradation. In addition, the solvent helps in viscosity control by lowering the viscosity of the reaction mixture. This makes mixing, stirring, and heat transfer much easier. Finally, the solvent can act as a chain transfer agent, which limits polymer chain growth and helps control the molecular weight of the polymer. Next, I will explain the essential conditions required for solution polymerization. A suitable solvent must be chosen so that it can dissolve the monomer and polymer, remain inert, and have a suitable boiling point. The concentration of monomer and initiator must be controlled because it affects the reaction rate and polymer properties. Temperature and agitation are important to maintain a consistent reaction and uniform mixing. High purity of materials is required to prevent reaction inhibition. Finally, if a solid polymer is needed, solvent recovery is required after polymerization. Next, we go to advantages and disadvantages of solution polymerization for polyethylene. Advantages of solution polymerization. Firstly, efficient heat removal. Heat is efficiently removed through solvent reflux, preventing overheating. Secondly, viscosity control. The inert solvent reduces viscosity, allowing uniform heat transfer during polymerization. Thirdly, easy processing. Lower viscosity makes heating, stirring, and overall processing easier compared to bulk polymerization. Lastly, high monomer conversion. The process typically achieves 80 to 90% conversion of monomer into polymer. Next, disadvantages of solution polymerization. Firstly, high cost. The use of expensive solvent increases overall production costs. Secondly, lower molecular weight. Solvent can act as a chain terminators, resulting in polymer with lower average molecular weight. Thirdly, environmental impact. Solvent release may cause environmental pollution if not properly managed. Lastly, lower product purity. The final product has lower purity compared to bulk polymerization due to solvent residues. Next, I will explain the products and application of polyethylene produced by solution polymerization. First, high density polyethylene or HDPE is known for its high strength and chemical resistance. It is commonly used in pipes and tubing, containers, and industrial bottles, as well as blue molded products. Next, linear low density polyethylene or LLDPE is flexible and tough. Its applications include plastic film and flexible packaging, stretch wraps and pellet wraps, and agricultural and industrial film. Finally, ultra-high molecular weight polyethylene or UHMWPE is extremely tough and highly wear resistant. It is used in medical implants such as joint replacement, high-performance fibers, rope and protective gear, and conveyor belts and other wear resistant components. Next, we go through to the third method of polymerization, which is emulsion polymerization. This method is different from bulk and solution polymerization because the reaction is carried out in a water-based system. Emulsion polymerization is a polymerization process that is carried out in water as the continuous phase. In this method, the monomer is dispersed into small droplets with the help of surfactants or emulsifiers. A water-soluble initiator is used to start the polymerization reaction. Most of the polymerization occurs inside micelles rather than in the monomer droplets. In polyethylene production, this method is not widely used for bulk polyethylene due to the low solubility of ethylene in water. However, emulsion polymerization is applied to produce polyethylene latex and aqueous dispersion for coatings, adhesive and surface applications. Next, I will explain the essential principle and factors involved in emulsion polymerization. First, the process uses water as the aqueous medium, which acts as the continuous phase. This helps in better heat control and improve safety during the reaction. Next, surfactants or emulsifiers are added to stabilize the monomer droplets. These surfactants also form micelles, which are the main site where polymerization occurs. The reaction is then initiated using a water-soluble initiator, which generates free radicals in the aqueous phase. During the process, the monomer diffuses into the micelles and polymer particle grows inside these micelles. In addition, several factors affect the efficiency of emulsion polymerization, including the type and concentration of surfactant, the type and decomposition rate of the initiator, temperature and pressure, emulsion stability, and the monomer diffusion rate. I will discuss the advantages and disadvantages of emulsion polymerization for polyethylene. Advantages of emulsion polymerization. First, emulsion polymerization is environmentally friendly because it uses a water-based process which reduces the use of organic solvents. Second, it has a low viscosity system which allows better control during the polymerization process. In addition, it provides excellent heat control as water allows efficient heat transfer and prevents overheating. Finally, this method can produce high molecular weight polyethylene, resulting in good strength and durability. However, there are also some disadvantages. Surfactant used in the process may remain in the final product, leading to the lower polymer purity. The recovery of solid polymer is complex and energy intensive. Also, due to the high water content, the polymer heat reactive volume is lower. Lastly, emulsion instability may occur if the reaction conditions are not well controlled. Next, I will show examples of products and the application from emulsion polymerization of polyethylene. The first product is polyethylene latex. It is commonly used in water-based coatings as well as in adhesive and binders. Another product is polyethylene wax dispersion. This product is mainly applied in paper and cardboard coatings to improve water and grease resistance. It is also used in polish and surface protection formulations.
So I will present about suspension polymerization of polyethylene. Suspension polymetry is a method used to produce polymer in the form of solid bits. Ethylene monomers are dispersed in liquid medium, and this method is used to produce polyethylene with good control over particles. How suspension polymerization works? So first, ethylene and indicator are added into a aqueous medium. Then continue stirring to break the monomer into small droplets between 1 to 10 micrometers. Then polymerization occurs inside the monomer droplets. And lastly, solid polyethylene bits are formed at the end of the process. So for fundamental of suspension polymerization is water is used as the reaction medium and helps it in heat removal. Then second, stabilizers are added to prevent the droplets from merging. Third, particle size depends on the stirring speed. Fourth, temperature is easier to control compared to bulk polymerization. And lastly, oil-soluble initiators are used to start the polymerization reaction. So, this method has advantages and disadvantages. So, for advantage, it's economical and environment friendly. Also, it allows the bed for better temperature control compared to bulk polymerization. This because bulk polymerization must at high temperature to solve it. Also, however, the disadvantages is stabilizers are required the process. The process is more complex than bulk polymerization. Lastly, it less commonly used for large-scale polyethylene production. For product and application, polyethylene produced by suspension polymerization is commonly used in household applications, especially in the kitchen. Example, plastic bottles, food container, and it's also used in more products such as toys, trays, as well as laboratory plastic like tubes and beakers.
The gas phase polymerization method for polyethylene production is an industrial process where gaseous ethylene monomer is converted into solid polyethylene polymer within a reactor without the use of solvent or liquid diluent. The reaction occurs to the surface of a solid catalyst, typically in a fluidized bed reactor. This method is commonly used to produce HDPE and LLDPE with a good control over polymer properties. For core principles, first of all, heterogeneous reaction. The process is inherently heterogeneous, with the polymerization occurring on the surface of solid catalyst particles that are suspended in a gaseous stream. The second one is mass transfer. Monomer gas must continuously diffuse to the active sites within the growing polymer particles to sustain the reaction. The third one, heat transfer. Polymerization is highly exothermic, so efficient heat removal is critical to prevent hot spot, catalyze deactivation, and the melting or fusion of polymer particles, which is agglomeration. And for condition, the first one is temperature. The temperature is carefully maintained below the polymer softening point and below the dew point of the monomers or inert diluents to manage heat and prevent the bed from collapsing, but high enough to maintain reaction kinetics. The second one is pressure. High pressure generally favors higher reaction rates and molecular weight by increasing monomer concentration. Pressures can range from standard atmospheric pressures to tens of bars. The third one is catalyst type. The choice of catalyst system detects the required operating window and the type of properties of the final polymer product. For advantages, first one is high purity. Polymers are obtained in high purity as no solvent or emulsifiers are present. The second one is no viscosity issues. Absence of a liquid medium prevents viscosity build-up, allowing for high molecular weight and better control over product properties like comonomer incorporation. The third one is energy efficiency. Lower operating temperatures and no solvent evaporation reduce energy consumption. Last but not least, versatile products. Excellent for making a wide range of polymers, including impact core polymer, which is IPC. For these advantages, the first one is finest carryover. High gas velocities needed for fluidization and heat transfer can carry fine polymers particles out of the reactor, causing blockages. The second one is particle control, preventing agglomeration and ensuring uniform particle size and distribution requires precise control of gas flow. The third one is catalyst dependency. For performance heavily relies on advanced catalyst technology to manage reaction rates and product quality. And last but not least, example of products and application of gas-phase polymerization. For linear low-density polyethylene, we got stretch and packaging film. There are good flexibility and high tear resistance, and plastic bag, tough and impact resistant for daily use. And for high-density polyethylene, we got bottles and containers. It is high stiffness and chemical resistance. Crates and drums are strong and durable for heavy-duty use.
This slide presents a comparison of 5 polymerization methods: bulk, solution, emulsion, suspension, and gas phase polymerization, based on heat control, reaction medium, and product purity. In terms of heat control, bulk polymerization has poor control, while solution, suspension, and emulsion polymerization provide better heat management. Emulsion polymerization has the best heat control, whereas gas phase polymerization shows a medium level. Regarding the reaction medium, bulk polymerization uses pure monomer. Solution polymerization use solvents, emulsion and suspension use water, and gas phase polymerization involve gas and a solid catalyst.
For product purity, bulk and solution polymerization produce high purity polymers, while emulsion, suspension, and gas phase polymerization produce medium to high purity products. Looking at the strength and weakness, solution polymerization offers good heat transfer and uniform polymers, but requires solvent recovery. Second, bulk polymerization provides high yield and fewer impurities, but suffer from poor heat control. Thirdly, emulsion polymerization has excellent heat control and can produce high molecular weight polymers, but require complex purification. Next, suspension polymerization allows good heat control and easy polymer separation, but is not suitable for gaseous monomers like ethylene. Last but not least, gas phase polymerization is cost-effective and efficient for large-scale production. Although catalyst deactivation may occur, this slide shows the suitability of each method for polyethylene production. Solution polymerization is used for high-purity applications such as LDPE. Bulk polymerization is limited to small-scale production. Emulsion polymerization is mainly used for rubber and latex, while suspension polymerization is suitable for PVC and not PE. Gas phase polymerization is the most widely used industrial method for PE, especially for LDPE and HDPE. In conclusion, gas phase polymerization is the most advantageous method for polyethylene production due to its low cost, high efficiency, good product quality, and environmental friendliness. Therefore, it is the preferred method for large-scale industrial PE manufacturing.
In conclusion, bulk, solution, emulsion, suspension, and gas phase polymerization each offer distinct advantages depending on the type of polymer and desired product properties. The selection of polymerization method significantly influences molecular weight, thermal control, particle size, and overall product quality. Overall, bulk and solution polymerization are suitable for simpler systems. Emulsion and suspension polymerization provide better heat control and particle formation, while gas phase polymerization is highly efficient for large-scale industrial production, particularly for polyethylene due to its cost effectiveness and environmental benefits.